Over to you. Thank you.
Thank you very much for the introduction. Yes, I would like to present to you some aspects on the cyclic deformation behavior of Invar alloys additively manufactured by wire-based DED process. So, firstly, iron and nickel-based Invar alloys are a group of functional materials that exhibit a very low coefficient of thermal expansion. Especially the binary iron-nickel alloy containing 36% of nickel shows the lowest CTE values. As these alloys are potentially applied in safety-critical fields that contain intricate cyclic loading conditions, the knowledge about the structural integrity of these alloys are, of course, paramount. You see here the composition of the filler metal we used, and you see this contained about 34% of nickel and also about roughly 2% of niobium, which will be paramount or very important in the remainder of the presentation. So, the material has been processed using the DED LB as well as the DED arc process, and we manufactured some plain cubes and extracted the specimens via EDM. For the DED LB experiments, we used a ProFocus 1000 deposition head from Oscar PLT. This one has a special configuration as it uses 6 separate diode lasers, and it allows the additional heat input by using the hot wire current. So this was set to 40 amps, and this just introduces some additional heat to the actual laser power. So for the DED arc experiments that were performed according to the gas metal arc welding process, we used a welding robot by Close. So the microstructure has been assessed firstly using the EBSD techniques, and these IPF maps with the superimposed image quality show some major differences in the microstructure, because in the DED arc material we see large elongated grains that align along the building direction, and they exhibit this typical 001 strong crystallographic texture in build direction. The DED LB process material is characterized by a slightly lower crystallographic texture. The grain aspect ratio is slightly lower, and I think the overall microstructural evolution can be discussed based on the setup that uses 6 different separate lasers in the deposition head, and also the utilization of the hot wire current heat input just promotes some grain growth that deviates from this 001 orientation along the build direction. Complementary, the microstructure has been assessed using the BSE contrast, and in line with the EBSD findings, we see large elongated columnar grains, as well as a second phase that precipitates mainly on the grain boundaries. And therefore, we performed EDS measurements, and these allow for the analysis of these precipitates, and they can be identified as niobium carbides. So niobium, as I mentioned, about roughly 2% were additive filling wire, and this is usually done to reduce the hot cracking susceptibility of these materials. Moreover, the niobium carbide has the positive effect that it yields extraordinary mechanical properties as determined by tensile testing. As you see here, yield strength and ultimate tensile strength are well about 400 or more than 500 megapascals. And the DED LB condition is slightly increased in strength and ductility, which can be attributed to the decreased crystallographic texture according to the well-known Hall-Patch relation. I would like to discussed it in the context of a previous study on PBF LB processed Invar alloy that does not contain niobium and hence no niobium carbides, and we see here that the ductility is significantly increased on the expense of the strength. And these monotonic properties are important as we discuss the fatigue properties. So in order to assess the fatigue life, total strain controlled fatigue tests have been performed using 3 different strain amplitudes. And the first thing we saw that these tests are highly reproducible and the material is not characterized by a large scatter. And what we see that at all tested strain amplitudes, the DAD arc material shows superior fatigue life compared to the DAD LB material. At the higher strain amplitudes, the strain lives are somehow converging, but the difference is more pronounced at the lower strain amplitudes of 0.35%. I would like to compare this again to the previous study. And what we see here is that at the highest strain amplitude, here, the powder bed fused Invar alloy that is characterized by the highest ductility shows the best fatigue life at the high strain amplitudes. At the low strain amplitudes of 0.35%, the DAD arc material is still characterized by the highest fatigue life, and as this somehow is the transition to the high cycle fatigue regime, this can be associated to the increased monotonic strength of this material. However, the DAD LB material is still showing the lowest fatigue life, and in order to elucidate that, we have to analyze some more data that has been acquired during the fatigue testing. So firstly, what we see here are the cyclic deformation responses, so the strain amplitude versus the number of cycles. And it can be seen that the material does not show any significant or pronounced hardening or softening during testing. And we see that especially at the lower strain amplitudes, the DAD LB material, according to the monotonic strength, shows higher cyclic stress amplitudes compared to the DAD arc material. Then at the higher strain amplitudes where the fatigue lives are converging, we see an almost similar stress level during cycling. Further, we analyzed the cyclic stress strain hysteresis, and in good agreement with the cyclic deformation responses, we see that at the high strain amplitudes, the cyclic stress strain hysteresis is almost identical, but, and this is somehow special, at the lower strain amplitudes, where the DAD arc material is almost deformed, or predominantly deformed elastically, the hysteresis loop for the DAD LB material is significantly wider, and usually this is a measure for the fatigue damage or also for the dissipated energy per cycle, and thereby for the irreversible plastic strain. This can be also seen here. Here we plotted the total plastic strain versus the number of cycles. And this is also consistent with the previous results, as you see that at a certain total strain amplitude, the plastic strain amplitude for the DAD LB material is significantly higher, and so the lower fatigue life at all strain amplitudes can be explained. Further, of course, we analyzed the porosity using computer tomography. What we see here is that the relative density is relatively high, but the DAD arc material shows larger defects and a slightly decreased relative density compared to the DAD LB material. However, when looking at the fracture surfaces, first we see clearly the crack initiation, crack propagation, and final overload fracture areas. But we did not observe any crack initiation on porosity, which means that the fatigue life is not governed by the process inherent flaws, but this indicates more that the material shows some very high damage tolerance towards these pores. So, finally, I want to show you some results on still ongoing research. So, in order to explain the fatigue behavior, we conducted TEM measurements. And similar to the EBSD results, we see certain differences in the both conditions. Firstly, we see some intergranular, these are intergranular niobium carbides. So these are not only aligned along the grain boundaries, but also inside the grains. They are slightly bigger within the DAD arc condition. And we see that they seem to have an impact on the overall dislocation mobility. Because in the DAD-LB condition, we see that the relatively smaller niobium carbides seem to hinder the dislocation mobility, which is much higher in the DAD-ARC material, and therefore we see such a typical arrangement of the dislocations in cellular arrays. But here, further research is necessary regarding the other highest strain amplitudes and also the initial state. So, therefore, I would like to thank you for your attention and for the respective funding. Thank you.
Thank you very much, Johannes. Any questions? There's a lot to take in. Here we go, I'll run the microphone over to you.
Thank you for your talk. Could you share any insights about why the different processes would have produced different grain sizes, and were you controlling for interpass temperature or anything like that to try to maintain more consistency between the two processes?
There is not much fundamental knowledge about the microstructure evolution when using this particular laser deposition head and with the superimposed impact of the hot wire current. This is usually used in welding applications to increase the deposition rate and so on, but this is still ongoing research, but it's always discussed as it has an impact on the magnitude and principal direction of the thermal gradient, and it impacts the ratio of the thermal gradient and the cooling rate. Okay.
Anybody else? Where can we follow and find out more?
ResearchGate?
As your research.
No, so it is still ongoing research. I don't know, we have to come to an end finally, but we are also planning for Additive Manufacturing Journal or something like that, and MSE, MS&T, wherever. Yeah.
Perfect. Thank you very much.
Okay, thank you.